Hello students, welcome to the lecture series of fluid mechanics. Myself, Professor Dhruv Patel. In last lecture, we have learned about examples based on Buckingham pi theorem. Now in this lecture, we will learn about various types of models, prototypes, Reynolds Model Law and examples based on it. So first of all, what do you mean by model analysis? So, for predicting the performance of any large structures like dam, spillways, or any machines like turbines or pump, before actually constructing or manufacturing any machine or large size structure, we have to make models of that machines or structure, and then tests are performed on that model and obtain desired information. That is known as model analysis. So first of all, so what do you mean by model? So model is basically small scale replica of actual size structure, right? And what is the prototype? The prototype is actual size of machine or structure, that is known as prototype, right? So what are the basic advantages of this method? Models analysis, what are the basic advantages of it? So first one is performance of any machine or structure can be easily predicted before manufacturing it. Second one is relationship between various factors affecting on it can be determined. Third one is alternative designs can be verified and optimum designs can be obtained. So as you know, model analysis and is one kind of trial and error method. So by this method, you can also optimize your result by constructing models of 2 or 3 times. Last one is for model testing, useful information about prototype performance can be obtained. On models, we can perform many types of testing. So we can compare model and prototype and we can predict prototype performance also. Yeah. So let us discuss further things about model analysis. So here are some basic forces which are considered in model analysis. So first one is inertia forces. So what do you mean by inertia forces? So basically it is equal to the product of mass into acceleration to the flowing fluid. It is known as inertia forces. Next one is viscous forces. The forces due to viscosity effect, that is known as viscous forces. Viscous forces generally occurs opposite direction to the flow. Third one is gravity forces. The downward side force from any direction, that is known as gravity forces. It is also basically mass into acceleration. Then pressure forces. The pressure forces we have already learned about Pascal's law. It is always applicable to the cross-sectional area. Surface tension we have already learned. It is tensile force acting on surface of water when it is separated from another medium. Last one is elastic force. So it is equal to the product of elastic stress and area of the flowing fluid, that is known as elastic force, or you can say force within the elastic limit, that is known as elastic force, right? For memorizing all these forces in sequence, you have to simple remember this short form IVGPSE. Remember students, I again repeat IVGPSE. That means inertia, viscous, gravity, pressure, surface tension and elastic forces. Clear? So by this shortcut method, you can easily remember various types of forces. Now various types of dimensionless number based on it. So you have to remember sequence of that forces. Then after you can derive equation of that dimensionless numbers. So let us revise equation of forces IVGPSE. That means inertia, viscous, gravity, pressure, surface tension and elastic force. Our first number will be Reynolds number. So basically Reynolds number, that means first force divided by second force. So inertia divided by viscous. Clear? So inertia force divided by viscous force. Second number will be Freud number. So Freud number, that means first force remain as it is and divide by third one. So first divided by third, inertia divided by gravity, that means Freud number. Next one is Euler number. So first inertia remain constant. So inertia divided by pressure force. So first divided by third, that is known as Euler number. Fourth one is Weber number. So for Weber number, first divided by 5, inertia force divided by surface tension force. And for last Mach number, for Mach number you have to divide inertia force to the elastic force. Clear? So if you remember these forces in sequence, you can easily remember various types of number. So for Reynolds number, first force divided by second. For Froude number, first force divided by third. For Euler number, first force divided by pressure. For Weber number, first force divided by surface tension, and for Mach number, first force divided by elastic force. So you have to just remember these forces in sequence. Clear? Here you have to remember in Reynolds number there is no any under root. In all other number you have to do under roots in their respective equations. Clear, students? So this is all force divided by various types of forces. So this all number is dimensionless number which is used in analysis of model and prototype. Now let us understand various types of similarities. So similarity means various models and prototype have similar property. By testing models, we can evaluate prototype also. That is known as similarity. Clear? So first we have to do testing on model. If the model and prototype is in similarity, so all the forces, all the values applicable to model is also applicable to prototype. That is called similarities. Basically, there is three types of similarities: geometric similarity, kinematic similarity, and dynamic similarity. So first one is geometric similarity. So for geometric property, we all know this: length, width, height, area, volume, that all are geometric property. The geometric similarity is said to exist between model and prototype. The ratio of corresponding linear dimensions in the model and prototype should be equal. So for example here, length of prototype divided by length of model is equal to length ratio. Width of prototype divided by width of model is equal to width ratio. Diameter of prototype divided by diameter of model is equal to length ratio also. So all the ratio for model and prototype will remain same. This is applicable to area also and volume also. For area, area of prototype and area of model will remain area, that means length into width, length into width. So that is considered as length ratio. Clear? So that is it from geometric similarities. Next one is kinematic similarity. So in kinematic similarity, ratio of the velocity and acceleration in the corresponding points in model and prototype will remain same. For example, velocity of prototype divided by velocity of model, or velocity of prototype at point 2 and velocity of model at point 2, the ratio remains same. For acceleration, that is acceleration of prototype divided by acceleration of model, that is known as acceleration ratio. Third similarity is dynamic similarity. So in dynamic similarity, ratio of various types of forces acting on corresponding model and forces should be same. That means any type of forces. You can take inertia forces ratio also, you can take elastic forces also, you can take viscous forces also. All ratio remain same. That is known as dynamic similarity. So basically there is three types of similarity. In first type, geometric type, that means length, width, height, area, volume, all ratios will remain same. Second type will be kinematic, in which velocity and acceleration ratio will remain same. And third type will be of dynamic, in which forces will remain same. Right? Now let us move on important theory. It is Reynolds Model Law. So what do you mean by Reynolds Model Law? So first of all, Reynolds Model Law based on Reynolds number. Here Reynolds number we have to remember. We can derive Reynolds number also in chapter number 8. But here we have to remember Reynolds number, that means rho Vd divided by mu. Rho Vd divided by mu, in which rho means density, V means velocity, D means diameter, and mu means dynamic viscosity. Instead of diameter, you can also write rho VL divided by mu. Unit remains same. Clear? If you derive unit of Reynolds number, it will become unitless parameter. You can try this at home. Rho Vd divided by mu. Try to derive unit of this, it will become unitless parameter, right? So first of all, what do you mean by Reynolds model law? Reynolds model law, that means Reynolds number of model is equal to Reynolds number of prototype. So it is one kind of similarity purpose. So Reynolds number of model, that means row of model, velocity of model into length of model divided by mu of model is equal to rho v d by mu of prototype. Here instead of diameter you can also write length also, right? If we divide this row of prototype, velocity of prototype and length of prototype divided by row of model, velocity of model and length of model into 1 divided by dynamic viscosity of prototype divided by model is equal to 1. So here it is considered as rho p by rho m, ratio of densities of prototype and model, that is known as density ratio. So it is density ratio, then velocity ratio, length ratio divided by dynamic viscosity ratio is equal to 1. So this is simply a Reynolds model law. For practical purpose, we have to remember this equation: Reynolds number of model is equal to Reynolds number of prototype. Clear? For better understanding, let us solve one or two example based on Reynolds model law. So first of all, this example, here you have to select data very carefully, because some data is only for model and some other data is only for prototype. So you have to select data very carefully. First of all, a pipe of 1.5 meter diameter is required to transport an oil of a specific gravity 0.9. A dynamic viscosity of 0.03 poise at the rate of 300 liter per second. The tests were conducted on up to this limit, up to this data. We cannot say that data is for model or data is for prototype, right? But let us read further. The tests were conducted on 15 diameter pipe. The tests were conducted, that means further data will be for model only. So above data from this line will be for prototype only. So here we can write diameter of prototype 1.5 meter, then specific gravity S of prototype 0.9, dynamic viscosity, that means mu of prototype 3 into 10 raised to minus 2 poise, discharge of prototype 3 meter cube per second. Here they have given 3000 liter per second. We will directly convert liter per second into meter cube per second, 3 meter cube per second. Now for model, 15 diameter of model 15 that means 0.15 meter, 20 degrees Celsius temperature, it is not necessary. The viscosity of a water is 0.01. Water, that means model. Tests were conducted on water. So viscosity of model, that means 0.01. Mu of model is 0.01 poise. Find out velocity and rate of flow in model. So we have to find out velocity, that means velocity of model, and rate of flow, that means discharge in model. Clear students? We have to find two quantities, velocity and discharge of model. So first of all, solving this any type of example like model and prototype, you have to apply Reynolds model law. So according to Reynolds model law, Reynolds number of model is equal to Reynolds number of prototype. So rho v d by mu for model is equal to rho v d by mu for prototype. Here rho of model is given, diameter is given, mu is given. Rho, diameter and mu is given. So we can find ratio of Vm by Vp. So here by putting all this value from given data, ratio of Vm by Vp is equal to 3. Here this will become our equation number 1. Let us solve discharge Qp. Here discharge Qp is already given. So discharge Q is equal to area into velocity V. So velocity of prototype is equal to discharge of prototype divided by area of prototype. Discharge of prototype, that means 3, this is already given, and area of prototype, that means pi by 4 diameter of prototype square. That means 3 divided by this data. So velocity of prototype will be 1.697. Here this value of Vp will be put in this Vp by Vm by Vp ratio. So Vm is equal to 3 into Vp. So Vm will be 5.091. It is our first remaining data. Next one is we have to find out Qm, discharge through model. So discharge through model is equal to area of model into velocity of model. That means pi by 4 d square of model into velocity of model. So we can find out discharge in liter per second. First we will get discharge in meter cube per second, 0.0899 meter cube per second. If you want to find discharge in liter per second, then you have to convert meter cube into liter by multiplying it by 1000, but it is not necessary. So 0.0899 will be your final answer of Q of model. Clear? So let us solve another examples based on it. A ship of 300-meter long move in a seawater whose density is 1030 kg per meter cube. A 1 gem 100 model of this ship is to be tested in wind tunnel. Now read this sentence again, students. 1 gem 100 model of this ship is to be tested in wind tunnel. That means model is to be tested in wind tunnel. That means the wind related data is for model and sea water related data is for prototype. Clear? So let us write here a ship of 300-meter long. So length of prototype 300 meter, density of prototype 1030 kg per meter cube. 1 gem 100 model of this ship. 1 gem 100, that means length of prototype is 300. So length of model will be 1 by 100 into 300. So 3 meter. The velocity of the air, for air that means model, the velocity of the air that means 30 meter per second. So Vm, 30 meter per second. The resistance of the model is 60 Newton. Fm, resistance, that means one kind of force which will mentioned in Newton. So Fm will be in Newton. Determine the velocity of ship in seawater. Seawater, that means prototype. So we have to find velocity of prototype Vp. Also resistance of the ship in seawater. That means we have also find Fp, resistance to the ship water. The density of the air. For air, that means model, the density of the model rho m is equal to 1.24. Kinematic viscosity, that will be nu in meter per second. For seawater, that means for prototype 0.012 strokes. Kinematic viscosity of prototype is 0.012 strokes. We have to convert strokes into meter square per second. So one stroke is equal to 10 raised to minus 4 meter square per second. So here 0.012 into 10 raised to minus 4 meter square per second, right? And viscosity for the air, that means for model, is 0.018 stroke. That means 0.018 into 10 raised to minus 4 meter square per second. So in this type of example, remember students, you have to first find out which data is for prototype and which data is for model. By this line, we can find that wind related data is for model and seawater related data is for prototype. Clear? Now let us solve our examples. We have to find velocity and forces for the prototype. So according to Reynolds Model Law, Reynolds number of model is equal to Reynolds number of prototype. So here rho v d by mu for model is equal to rho v d by mu for prototype. Now here mu is equal to dynamic viscosity. In our given data, they have mentioned kinematic viscosity. So in the Reynolds number equation, mu by rho, we can say this mu by rho, and here mu by rho, we can write mu by rho as kinematic viscosity. So equation will become velocity into length divided by kinematic viscosity. Clear? Velocity into length divided by kinematic viscosity. We have to find velocity of prototype. So all other data is already given in the given data. So if you put all other values from given data, we will find velocity of prototype is 0.2 meter per second. Yeah. So velocity of prototype is equal to 0.2 meter per second. Now resistance of the prototype. So we can also write resistance as rho L square V square. Force F is equal to rho L square V square. If we derive equation of rho L square V square, then remember it, for rho equation will be kg per meter cube. For L square equation will be meter square. For velocity equation is meter per second. but velocity square, so meter square per second square. So here what is remaining? Meter cube got cancelled. So in above side kg per meter, kg into meter per second square, that will be considered as force in Newton. Clear students? So here we can write force ratio of prototype divided by force of model is equal to rho L square V square of prototype divided by rho L square V square of model. Here expect from force of prototype, all other data is already given, so you can find Fp is equal to 22150.2 Newton. Clear student? So in this type of example you have to just use Reynolds model law and compare model and prototype for various data.